welcome to our video about inverse exponentials. Before us, we see all of the parent graphs that we've been working with, so we're going to talk about the parent graph and figure out the inverse equation.
All right, so our parent graph here is for the y equals x squared, which we know the pattern is 1, 1, 2, 4, 3, 9. And that's our parent graph or quadratic. So we're going to talk about the inverse. And remember, inverse, we're swapping the x and the y. So I'd say x equals y squared. And I want to get the equation so it's equal to y. So to undo a squared, we're going to square root both sides. So my square root undoes this square. And so I'm square rooting x. Remember, when we square root, we could do a positive or a negative. So it could be the positive or the negative of square root of x equals y. To put it on our graph, we know that we switched our x and our y values. So my vertex is still the 0, 0. But now, instead of 1 over and 1 up, we're going to go 1 up, 1 over. 1 down and 1 over. And then instead of 2 over, 4 up, I'm going to go 2 up and 4 over. And that's the same with down 2 over 4. Instead of over 3, up 9, we're going to go up 3 over 9. So our new graph for our inverse equation is this.
And here you can see the positive square root of x. If you just cover the bottom part, you can see the positive square root of x on top and then the negative square root of x graph on the bottom, which together makes our sleeping parabola that we've been working with. The next one, we have y equals x, which is just a linear graph. So x equals y, so we'll have 0, 0, 1, 1, 2, 2, 3, 3, etc. We'll have a nice diagonal line for our parent graph. And the same works with our negative values as well. If x is -1, then y is -1. If x is -2, then y is -2. So we'll also have our line continue on down.
Remember, we switch our x and our y's, so the inverse of this equation is x equals y instead of y equals x, which is essentially the same equation. So that means our inverse graph is identical to our first graph, so we're just going to draw straight down the same line.
All right, let's check out this cubic graph here. Remember, with the cubic function, my locator point is here at 0, 0. We learned that that's our inflection point where our cubic graph kind of curves. And then if I go 1 cubed is just 1, so that means I go over 1, up 1. And then if I do -1 instead, -1 all cubed is -1, so I go left 1, down 1. All right, continuing this pattern, we can plug in a 2. So if I plug in a 2, that means 2 cubed is 8. So that means from my locator point, I'm going to go right 2 and up 8. And then in the other direction, we'll go -2, and -2 all cubed is -8. For our inverse equation, we're just going to do that same strategy of flipping our x and our y. So now we have x equals y cubed. However, when we're writing equations, we usually write it in the form y equals. So if we want to set this to y equals, let's cube root this side and cube root this side. The cube and the cube root undo each other, so you're just left with y equals, and we have the cube root of x. All right, what does that mean for our graph? We can use that y equals x strategy and do that symmetry to reverse our graph, or we can flip our x and y coordinates. All right, now that we have our points, we can connect them. And we see we kind of have this sideways stretched out S. All right, let's check out the absolute value graph. We know a parent graph for the absolute value is just a nice V shape. So our locator point is here at 0, 0. That is our vertex of our V. And then we know that our V shape is just going to go over 1, up 1, over 2, up 2. It'll kind of look like our y equals x graph, but this negative part will be made positive instead. All right, doing our inverse here, we can just switch our x and our y. So now we have x equals the absolute value of y. This is a little interesting because if I want to get y equals, I have this absolute value bar going on. So I could rewrite this as x could equal a positive y, or x could equal a negative y. Since y could equal x or negative y could equal x, that's essentially saying the same thing we have up here, that x equals the absolute value of y. So that is our y equals form. So if we were to draw the inverse, if I use that line of symmetry, y equals x, I know that this will reline back up with itself, but then this will be reflected, and now our v will be going this way instead. With our square root of x graph, we have our locator point at 0, 0, which is kind of our start end point. And with the square root graph, we can pick perfect squares because we know when we square root them, we'll get whole numbers. So if I do the square root of 1, I get 1, so I know I'm going to go over 1, up 1. If I do the square root of 4, then I know I'm going to go over 4, up 2, because the square root of 4 is 2. After over 4, up 2, if we do the square root of 9, then we get 3, so we know we can go over 9 and up 3. Awesome, connecting these points, we have our square root graph.
So we do the inverse of our equation. I'm going to switch my x and y's. So now I have x equals square root of y. And I want to undo that. I want to make sure that I'm y equals my equation. So I'm going to undo the square root by squaring both both sides. So this squared gets rid of the square root. So now I have y equals x squared. So if you'll notice, y equals x squared is our parent equation for the parabola, but with our square root, we only have the one side. So we need to restrict our equation here. So we have y equals x squared, but then we need to add x has to be greater than or equal to 0.
And the reason why we restricted the domain here is because we can see that if I were to reflect this about y equals x, we're only going to have the 1/2 of the parabola, like Janice mentioned. And because our range of our original parent function is only from 0 on to infinity, that range now becomes our domain for the inverse. And so since our range is anything where x is greater than or equal to 0, now that becomes our domain for the inverse. So that's why x has to be greater than or equal to 0. So instead of going over 1 up 1, we're still going to go over 1 up 1. Instead of going over 4 up 2, now we're going to go over 2 up 4. And then instead of over 9 up 3, now we're going to go over 3 up 9. So now we can see here we have our parabola shape, but it's just restricted from x greater than or equal to 0, and that works with our y equals x symmetry going on. All right, let's check out our rational function here. We have y equals 1 over x. We know with a rational function, we're going to end up with some asymptote. So we have a vertical asymptote along x equals 0 and also a horizontal asymptote along y equals 0. You can plug in some points here. For example, 1 over 1 is equal to y. So we have a point here at 1, 1. If I go over 2, now it's up only 1/2. It's going to kind of trail down on this side. And then same with our negative values. Let's write the inverse equation of our rational parent graph. Here we have y equals 1 over x, and now we have x equals 1 over y. If I want to get this in the y equals form that we've been doing, I can put x over 1, and I can flip both fractions. So now I have 1 over x equals y over 1, and we know y over 1 is just the same thing as y. So our inverse equation is y equals 1 over x, which happens to be the same as our parent graph. So that makes sense, because if I were to reflect this over y equals x, I'm going to end up with the same graph. We highlight it over, it's right on top of each other, but the inverse and the parent graph are the exact same for the rational. All right, let's do this exponential one. We have y equals b to the x, and we chose a base of 2. We know with an exponential graph, we're going to have an asymptote, and so I'm going to have my asymptote right here at y equals 0. So we have our asymptote right here at y equals 0. That means with my graphing, I know my locator point is going to be just 1 above my asymptote here. And then if I have a base of 2, that means y equals 2 to the x power. So if I did 0, anything raised to the 0 power is just 1. So y equals 2 to the 0. When x is 0, 2 to the 0 is 1, so y equals 1. So I have a point here at 0, 1. And then 2 to the x power. If I plug in 1, 2 to the first power is 2. So I know I go over 1 up 2. If I plug in 2 for x, that means I go over 2, and 2 squared is 4, so I'm going to go over 2 up 4. If I plug in 3, 2 cubed is 8, so I go over 3 up 8. All right, so this is the parent form of our exponential graph, and we know it gets infinitesimally smaller and gets closer to 0 as it approaches y equals 0. All right, let's write our inverse equation. So I'm going to swap my x and my y, so now we have x equals b to the y. In this case, b would be 2. If we wrote this with a base of 2 instead, we have x equals 2 to the y. All right, if I try to solve this equation for y equals, we actually don't know how to do that. We don't know how to make a variable that's an exponent, not an exponent anymore. So this is actually as good as we can get it right now. X equals 2 to the y power. Although we can't write our equation in y equals form, we can still graph what this would look like. So if we use our y equals x symmetry, we know now our asymptote is going to switch from y equals 0 to x equals 0. And we know we have a vertical asymptote. And instead of our graph going up and swooping this way, now it's going to come here. This is where it's approaching the asymptote. It's going to cross here at 1, 0 instead of 0, 1 like it did with the parent graph. And then it's going to come up and kind of swoop out this way. So this would be the graph of our inverse equation.
Okay, our first question says, are any parent functions their own inverse? Explain how you know. So if we look at this first one, the parent function is not the same as its inverse, so that isn't the same. If we look here, see how we have both of our lines, green and blue, for our parent function and our inverse function on the same spot. So that one is. So yes, we do have some functions. One of them is our y equals x. Our next one we're going to look at. This one isn't, this one isn't, This one is not. But if we look up here, we have both blue and green in the same location. So our y equals 1 over x is also a function that's parent is the same as its inverse. And we know that because the graphs are the same. Our next question says, do any parent functions have inverse graphs that are not functions? If so, which ones? So let's look and see if there's ones that aren't functions. Remember, when we're determining a function, we do the vertical line test. So if I look at this inverse and I'm looking at the green, you can see that I'm touching my green in 2 spots if I draw a vertical line. So that vertical line test tells me that this inverse is not a function. So the y equals x squared inverse is not a function. This one, we still have a function because we have that vertical line test. The vertical line test, we're only touching that line once. We do it here, same thing, we're only touching once. Remember, we're looking at the green one, so if I look at this green one and I do a vertical line straight down, I touch there and I touch here. So I'm touching that absolute value twice, so y equals the absolute value of x's inverse is not a function. This one, our vertical line test works, we're fine. Up here, same thing, we don't have any issues. And then this one, same thing, we do not have any issues with the line test, so they are functions.